Our industry is a tricky one. And I'm not just talking about making components that go on a circuit board. I'm talking about the entire electronics industry as a whole. What's wildly popular one day is outdated and forgotten the next. So, for this reason, it's important that designers keep up with their education as well as the various available tools on the market. Two of these tools we will be discussing in this episode are the eDesignSuite from STMicroelectronics and Würth Elektronik's REDEXPERT. The eDesignSuite is a comprehensive set of easy-to-use design aid utilities that are ready to help you streamline the system development process with a wide range of ST products. There are different utilities within the program, including thermal electrical simulators for components, signal conditioning design tool, and NFC and RFID calculators, but we'll be focusing on the Power Management Design Center. We're going to be taking a look at the different tools within the Power Management Design Center, including Power Supply Design Tool, LED Lighting Design Tool, Digital Power Workbench, and Power Tree Designer. There's even a section dedicated to the new simulator for SMPS and analog ICs. Würth Elektronik's REDEXPERT is a free browser-based simulation and selection tool, and it is specifically built for power engineers. It assists with thermal simulations and DC-to-DC converter designs, includes a rated current calculator and an EMI filter designer, and it is the world's most accurate AC loss model that uses empirical lab data and not analytical equations. Our demo will also feature the built-in component selection feature, and in our example, we're going to be starting with the inductor selection. We'll end the episode with simulation results and comparisons, including AC losses, temperature rise, and efficiency impact. Listening to Würth Elektronik's What's Up Radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and the most recent advancements in power design tools. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.
My name is Manish Khandelwal, and I'm working as a product definition engineer in the IC support team at Würth Elektronik. With me today is Victor Ceron from STMicroelectronics. Just to set the scene for today's session, there's two parts. I'll be presenting the Würth Elektronik segment, covering our REDEXPERT design platform and how it solves one of the most overlooked challenges in power electronics, inductor selection. After my segment, Victor from STMicro will take over for his dedicated section. So let's make the most of our time together and let's get into it. Here's what I will cover in the next 25 to 30 minutes. We will start with a quick introduction to REDEXPERT, what it is and why it was built. Then we will look at the real challenge of the inductor selection and switching power supplies, and specifically why most engineers are working with incomplete data. From there, I'll walk you through REDEXPERT's AC loss model, how it works, and why its accuracy matters. We will then move into the live design example using the STMicroelectronics evaluation board, calculating inductance, running the selection, and validating performance. And I will close with our rated current calculator before handing over to the team. Let's go. REDEXPERT is a Würth Elektronik's free browser-based design platform built specifically for power engineers. No installation, no license fees, just open your browser and start designing. At its core, REDEXPERT does several things. First is the component selections. You can filter throughout thousands of inductors, ferrite beads, filter chokes, common mode chokes, based on the footprints, shielding types, inductance, DCR, saturation current instantly. Second, DC-DC converter design. You just enter your input voltage, output voltage, load current, switching frequency, and REDEXPERT recommends the optimal inductance and ranks all matching components for your exact operating point for that DC-DC converter. You can also design multi-stage EMI input filters and simulate insertion loss using real measured component models, not idealized curves only. Fourth, thermal simulation. You can calculate temperature rise under real operating conditions and visualize how inductance changes with current at different temperatures. And finally, you can also calculate your rated current, which I will come back to you at the end of this presentation. And more importantly, all of this are completely free at redexpert.w-online.com. But what really sets REDEXPERT apart is the accuracy of its loss models. And to understand why that matters, we first need to talk about the problem it was built to solve. As you know, the inductor is often described as the most challenging passive component to select in a switching power supply. And there is a good reason for that, because a poor inductor choice leads to cascade of problems: excessive heat and efficiency losses, core saturation that causes instability, unexpected EMI and noise issues, wasted PCB space from oversized parts, and most painfully, like costly design respins and delays. And here is, you can see the key insight. The traditional data sheets only gives us DCR and I saturation, but these two parameters represents only about 35% of the total loss picture. The remaining 65%, like the AC core losses and the AC winding losses, are simply not in the data sheet, and you can't see them and you can't calculate them with a standard Steinmetz approach under real switching conditions. So this is the fundamental gap that REDEXPERT was designed to close. Here you can see the REDEXPERT interface. This REDEXPERT will help you to select wide range of products from the Würth Elektronik portfolio, which includes EMC components, power magnetics, some signal and communication component, capacitors, resistors, optoelectronics, some quartz crystals and oscillators, shielding, and thermal management products. With the help of this REDEXPERT tool, if you go into the EMC components, you can select the ferrites for PCB assemblies, ferrites for cable assemblies, different range of common mode chokes, over voltage protections, EMC line filter, and filter inductors. If you are in need of power inductors in the magnetics, you go into this particular column, and there you can find the power inductors, PFC chokes, different range of transformers, and wireless power coils. Similarly, for the capacitors, we have MLCCs, XY caps, aluminum electrolytic, polymer, DC link, super caps, resistors, and etc. With the help of some design tools like an EMI filter designer, if you want to design your own EMI filter for your power supply, you can easily do that with the help of EMI filter designer, and you can create your own LC filter or CL filter or pi filter or T filter, whatever you need, a multi-stage EMI filter. You can easily design it with the help of EMI filter designer. If you just only wanted to calculate your lifetime of a capacitor, aluminum electrolytic capacitors, you can go into that particular design tool, capacitor lifetime calculator, and with the help of this tool, you can calculate the lifetime of that particular capacitor. So REDEXPERT will not only help you to select the components, but it will also help you in designs. Before we jump into the selection of power inductor in REDEXPERT, let's quickly recap the types of losses we are dealing with in a power inductor. We have two main categories: core losses and copper losses. Core losses comes in two forms: hysteresis loss, that is caused by the repeated magnetizing and demagnetizing of the core material, and eddy current losses, which caused by circulating currents generated within the core itself. On the copper side, we have DC losses, which are simply a function of the DC resistance, and AC losses, which depend on the core winding structure, frequency, and current waveform. The design goal is always the same: reduce the total losses and achieve the highest possible efficiency. And this is exactly where REDEXPERT is ideally suited to help quickly and effectively. The traditional approach to calculating core losses is the Steinmetz equations. It describes how the core loss depends on the flux density and frequency. However, it has significant limitations. It's only useful over a narrow frequency range, and it assumes sinusoidal waveforms, and it does not capture all operating conditions, and most importantly, it does not include copper losses. But on the other hand side, our Würth Elektronik AC loss model takes a fundamentally and more powerful approach, while Steinmetz approach works with idealized ring cores and sinusoidal signals, our model works with real components across all materials and core shapes. It accounts for air gap and fringing effects, winding structure, square wave voltage, triangular current, and DC offset also. That gives you total AC losses, combining both core and copper losses together. So this brings us to our accuracy. Our AC loss model has been validated across a broad operating range frequencies from 10 kHz to 10 MHz and duty cycles from 0.1 to 0.9. When you compare REDEXPERT accuracy against the Steinmetz approach, the difference is very clear, particularly as you move away from ideal sinusoidal conditions and across varying duty cycles. REDEXPERT maintains consistent accuracy where Steinmetz begins to break down on those conditions. This is the foundation of confidence when using REDEXPERT for real customer designs. REDEXPERT supports a wide range of converter topologies, not just the common ones you can work with. It supports buck, boost in both synchronous and non-synchronous mode, SEPIC for both single and coupled inductor variants, and a topology independent mode where you input the inductor current and the voltage directly. And this last option is specifically powerful for engineers who are working with the custom topologies that don't fit into the standard converter topologies. Now, let's bring this to REDEXPERT with a real design challenge. We are going to work with STEVAL 3601 evaluation board, which is from the STMicroelectronics, that uses a DCP 3601, a miniaturized synchronous step-down buck converter. And the CVM is a great example of how a complete industrial power supply can be designed with minimal components, just one IC, one inductor, a couple of capacitor and resistors. The specifications is given here. This is 36 volt input, 5 volt output, 1 ampere output current, switching frequency is fixed for 1 megahertz. And the challenge for us here is to select the optimal inductor for input of 24 volt, output of 5 volt at 1 ampere and 1 megahertz. Then we have to validate the losses and thermal performance in REDEXPERT. As you all know, the inductor plays a critical role here. So finding an optimal inductor is definitely a challenge because inductor sets the output ripple current that directly influences total system efficiency, also impacts PCB footprint and cost, and it is also critical for EMI filter effectiveness. So let's dive into this and find an optimal inductor for this particular design. Before we open REDEXPERT, let's do the manual calculation to understand what inductance values are we targeting. So when you put the input parameters in the numerical formula of inductor calculations, we get the inductance value of 13.2 microhenry. As this device is a synchronous buck converter, it does not require an extra diode, so the calculation is very simple and straightforward. But when you have a non-synchronous buck converter in your application and diode is required, the most often time in this numerical calculation, we forgot to consider the diode's forward voltage, but REDEXPERT does not. Let's see this with the same example, considering this as a non-synchronous buck converter, how it impacts. So here you can see we just consider as a non-synchronous buck converter where we put the same input and output values, and when we find the inductor value with the help of REDEXPERT, we found out this comes as a 14.6 microhenry. So, but in the numerical calculation, it was given as 13.2 microhenry. So where does this difference come from? This difference is coming from the diode's forward voltage, which was 0.7 volt, which was not considered in this theoretical calculation. But REDEXPERT always pay attention to that. So here you can see when we put diode voltage into the numerical calculations, we can get the same inductance value what we were getting it from the REDEXPERT, that is 14.6 microhenry. Now let's go into the REDEXPERT and select the right power inductor for the STEVAL board design. Okay. Let's go into the power inductors. Once you go into the power inductors, you can see at the left hand side you have a different topologies given. We select buck converter, as the STEVAL board is a synchronous buck converter. Let's select the topology as a synchronous putting all the values for the input and output voltage and current. Input voltage is 24, output voltage is 5 volt, output current is 1 amps, switching frequency is 1 megahertz. Let's select that. Ripple is 30%, and we click on update, and then it will update all the inductors. And when you click on the details, you can see the details like how much is the inductance is required here. It is showing the 13.2 microhenry is the optimal inductance required for this particular design. Also, it will show you the duty cycle, the ripple current, the peak current, and everything here. You can also see REDEXPERT not only showing a single inductor, but it will show you a range of suitable inductance value, which you can clearly see here on this filter from 9.24 microhenry to 17.2 microhenry. So now you can easily select the power inductor which can be fit in your design based on these data, and it will also show you all the losses, AC losses, DC losses, and total losses right next to each inductor. You can also filter out all these inductors with the basis of rated current, saturation current, ripple, switching frequencies, or the size or temperature. Anything you can easily do that. I will make a one filter here, like I will remove this internal parts, and there you can see it is showing me 245 inductors for this particular design, but we need to select a one inductor. As you can see, the value is 13.2 microhenry. I would recommend to go with the 15 microhenry inductor. So let's filter here. I will put it 15 microhenry. It will show me the 15 microhenry. The values is reduced from 245 to 82 numbers. Now still it is too much. We can also filter it based on the minimum losses or the minimum size. Let's do it with the size first. Maybe between 5 to 7 mm. We select the inductor which is having a length of 5 to 7 mm. That will reduce it to 20 items. Then I can sort and filter here with the minimal losses. So if I click it here, I can clearly see the minimum loss inductor, which I can see is like the 41 milliwatt, which is this XHMI inductor 6060 size. So if I select this, here you can see the AC losses, DC losses, and total losses along with the temperature rise for this particular inductor. Once you select any particular inductor, you can also see these graphs for inductance versus DC current, temperature rise versus DC current, and the impedance versus the frequency graphs. And with the help of slider, you can see the inductance drop at the particular load current. So we have a current of 1 ampere. So I have set it here, this slider at 1 ampere. So here on this particular column, you can see that inductance at 1 ampere. So this was 15 microhenry is the standard inductance which is given in the data sheet. But at 1 ampere, the inductance would be at 14.9 microhenry. You can filter with these as well. Also, you can change the temperature and see how much is the impact of your temperature on the inductance graph as well, that you can see. But that we will cover in the next slides when we go into the saturation things. So that is how you can filter and select the optimal inductor for your design. Also, here you can compare the different inductor from the different size. For example, I wanted to compare the 6060 size with 5050 or 5030. I can clearly see here that how much is the losses and how these inductors would behave. So use the REDEXPERT. It would be very easy for selecting a power inductor. Here you can see the full loss breakdown and the temperature rise estimate of the selected inductor. AC losses are 12.4 milliwatt, DC losses are 38.6 milliwatt, and the total losses are 41 milliwatt. On the other hand side, the P versus I output plot gives you a powerful overview of how total losses behave across full load range from light load to full load. This is especially useful for understanding efficiency at both low load and high load conditions that are two very different challenges in power supply design. Please note here that this plot does not yet include DC bias effect or DCM behavior, so it represents the baseline continuous mode loss picture. As we know, the AC losses are dependent on the AC ripple current. This means when the ripple is consistent, it does not matter if the DC current changes. and the AC losses will be the same. So here the converter works in CCM mode. This is the level of detail what you got from REDEXPERT, and it gives you real design confidence. Inductor saturation, which is an important consideration. REDEXPERT calculates ripple current based on the rated inductance value. However, it currently does not account for inductance roll-off caused by the saturation under DC bias conditions. This is an important limitation to keep in mind during design. Inductance roll-off due to saturation is not standardized across manufacturers and can vary significantly, typically ranging from 10% to 35% depending on the product series. As a result, an inductor that appears suitable based on its rated inductance may perform quite differently in real operating conditions. So what do we recommend here is to use REDEXPERT, because REDEXPERT provides a slider tool that allows you to manually evaluate the actual inductance at your specific operating point. It is strongly recommended to use this feature to verify performance under DC bias and ensure accurate design validation. Saturation versus temperature. Saturation behavior is closely linked to temperature and should not be considered constant. As the inductor operates under load, its temperature rises and the magnetic core property changes. And this directly impacts the saturation characteristics, including the effective saturation current. As a result, an inductor that performs well at room temperature may exhibit increased inductance roll-off or reach saturation earlier at higher operating temperatures. And why is it important? Because when you design only based on room temperature datasheet values, that can lead to inaccurate assumptions about real world performance. So what do we recommend here? We recommend here you to use REDEXPERT that enables you to visualize inductance versus current curves at user defined temperatures. And this allows you to evaluate how the component behaves across your full operating temperature range and confirm that it remains within the safe limits. This is a critical validation step that is often overlooked but can significantly improve design reliability. Now let's look at the final feature I want to highlight is the rated current calculator for today's session. Here is a question that comes up regularly. The datasheet specifies a maximum rated current, but that rating is based on the standard test condition, typically measured on a specific PCB with defined trace dimensions. So your PCB layout will almost certainly be different. Würth Elektronik has developed a thermal model that calculates the rated current of power inductors based on specific PCB trace dimensions. And this is important because thermal performance of an inductor is not just about the component itself, it's also about how heat is transferred to and from the PCB via the copper traces. This gives component and design engineers the ability to understand exactly how their layout decisions affect the current carrying capability of inductor they have selected. It removes guesswork and helps you design with confidence. Before I hand over to our partners at STMicroelectronics, let me leave you with the key messages from today's segment. Number one, traditional datasheets measures up to 65% of total losses. DC resistance and saturation current alone are not enough. Second, REDEXPERT uses real hardware measurement data, not simplified formulas, to give you the complete loss and thermal picture at your exact operating point. Number three, always verify inductance roll-off under load and temperature before finalizing your inductor choice. Use the REDEXPERT slider. Number four, PCB trace dimensions affect your rated current, so use the rated current calculator to validate your layout assumptions. And number five, REDEXPERT is completely free. There is no reason not to use it. So visit redexpert.we-online.com today and use the REDEXPERT. I'll now hand over to Victor from STMicroelectronics for his dedicated segment. Over to you, Victor.
Thank you everyone for joining us. I'm here to walk you through a small demo on our eDesignSuite and eDessign simulation tools. My name is Victor Serron. I'm part of the product marketing team here at ST. I manage the analog and power portfolio for the central US. And with that, let's begin. So first of all, I just want to first introduce you to ST's simulation tools. The main purpose of the simulation tools, of course, to help customers simplify their designs, to shorten the development cycles, and these are tools that are um, available to our customers. They are totally free. And first of all, we have many simulation tools, so you need to specify the application use case. We also have selection capabilities that with just a few pieces of data, we can help you select the best device from our portfolio. Then we actually go to an analysis in the time and frequency domain. This includes simulation results uh, that encompasses not only time domain plots, but also efficiency, power losses, and stability plots. Then we can take these preliminary outputs from our web tool. We can export them to our own EDSim simulation tool. This is a piece of software that you can install in your PC, completely free, very flexible, simple simulator. And with that, you can start tweaking your project. You can tweak the stimuli that you want to simulate. Again, very complete tool, especially for switch mode power supplies. Do a quick demo in the next few slides on eDesignSuite. Very simple tool to use. There's a online component of the tool, the eDesignSuite itself. Then we can export that to our own locally installed EDSim tool. Typical output of a project. Again, this is the web portion of the simulation tool. Again, it spits out a very preliminary schematic with real-life components and also preliminary simulation results that you can tweak. And more importantly, export to an. We're going to look into the capabilities of this eDesignSuite demo. First of all, why do we need a EDSim software? So first of all, we as electrical engineers may be more used to having PSPI simulators. You know, there are many different pieces of software available from multiple suppliers that can do SPICE simulators. Not only ST, but many other suppliers actually provide SPICE models, which is true for our signal conditioning devices. We actually provide models for that. But the capabilities of PSPICE may not be enough to do a practical simulation of switch mode power supplies. That's why we rely on pieces of software like EDSim. This is based on Simplis, which is created by Symmetrics Technologies. And this tool is 10 to 50 times faster than SPICE simulations for switching mode power supplies. So I don't know if you've tried at some point, maybe during school, to simulate a buck regulator using PSPICE. It's painfully slow, and sometimes the simulation does not converge. So that's the reason why we leverage other type of simulation tools for switch mode power supplies. EDSim, again, this is our simplest based simulator. It's on its own, it's a fantastic tool to simulate any kind of AC/DC, DC/DC switching mode power supplies. What makes it great is that it has tons of synergies with our own web-based eDesignSuite tools, and we're going to see more details on that. I'm going to just to give you a quick overview of the device that we're going to showcase here. This is our new value 36 volt 1 amp buck regulator. It's a brand new device. It is a cost optimized solution. It's a 36 volt 1 amp synchronous buck. You can see there's no external diode. It has a fixed 1 megahertz switching frequency, and it comes in two versions. LCM, which is low consumption mode, and NMM, which is low noise mode. So basically, it is a PFM for high efficiency at light loads, and PWM for more predictive ripple for noise-sensitive applications. This device also comes in dithering and non-dithering versions to help you by leveraging spread spectrum within the oscillator of the internal oscillator of the buck regulator, which helps with emissions testing. It comes in a very simple to use SAW23 package, as you can see here. Again, fantastic device. It has been very popular in industrial applications mainly. These are the 4 versions that we have. We talked about low consumption, PFM, low noise, PWM, and dithering. So again, four versions overall. And the typical applications, very simple to use device. There's going to be it's an adjustable device. So the DCP3601, you can set the output voltage by using a couple of feedback resistors. And we actually include some guidelines on the more popular output voltages like 5 volt and 3.3 volts. So you have a preliminary selection of inductors, input, output, and boot capacitors, and bootstrap capacitors. So again, we want to make this as easy as possible for customers to use. Very efficient device. Again, it's a buck regulator, so it leverages very high efficiency. In a very small footprint. So you can actually see here the total solution footprint in our STVAL 3601 CD1, which is the DCP 3601 evaluation board. And also a quick snapshot that on the thermal characteristics of the evaluation board. So you can see that the thermal plot here, the device performs very well, very high efficiency, even though the SAW23 package does not have a power pad, it still can perform at under industrial application conditions. And this device, even it's a 36-volt buck, is thought for industrial applications, typically applications that are powered from a 12 and 24-volt industrial buses, and for which you can see here a couple of block diagrams. These are, as you know, industrial is a very fragmented market, but 12 and 24 volts are very common voltage rails. And we actually have a pin-to-pin compatible higher current version of the DCP3601. It's the DCP3603, same pinout, same package, but this device is a 3 amp buck regulator. In addition to having a low noise mode and low consumption mode with and without dithering, we also offer an additional switching frequency, a 500 kilohertz switching frequency that is thought for more noise sensitive applications. And you can see still very, very tight solution size for both the 3601 and 3603. You can use the same layout, even the same BOM, while considering the limitations of both devices. Now let's showcase what eDesignSuite is capable of. So first of all, we are going to show how to download eDesignSuite and what it's capable of, and then we are just going to do a real life example. So first, what is so eDesignSuite also includes our EDSim simulation tool. So EDSim is a fast and powerful electrical simulation tool for switch mode power supplies and analog ICs. So what is great about EDSim, first of all, it's a simplest simulator, and the main use for a simple simulator is to help with switching mode power supplies. In this case, we're going to be simulating a buck regulator, our new DCP 3601, which is a 36 volt, 1 amp synchronous buck for industrial applications. And what is great about Simplex compared to PSpice is that Simplex was specifically designed to simulate very fast and quick switching mode power supplies. So maybe a few of you may have tried to simulate a buck regulator in PSpice. First of all, it can be very, very small, so the simulations may take a long time to spit out a result, or they may not even converge. So the simulation may just crash at the very end, so you may not have an actual result. That's the reason of why Simplex is the right tool to simulate switching mode power supplies. The tool is completely free. It's actually a tool that ST provides to its customer base. Very powerful tool. So this is a quick overview of the many devices that EDSim supports. So from isolated AC/DCs, non-isolated AC/DCs, buck-based, not isolated DC-DC buck regulators, LD drivers, also amplifiers, comparators, passives as TVSs, thyristors, FETs, and this list is always growing. ST is always looking to integrate more and more devices, especially new devices, to the capabilities of EDSim. So again, fantastic tool to use. Well, first of all, just a very quick tutorial on how to install. So if you go to the address www.st.com/edsim, you can actually download the software. Again, it's completely free. I recommend you to sign into our ST website. Of course, you will need to create an account beforehand, because that way it will make the process a lot easier. And not only that, our eDesignSuite web model can actually store your latest project, so you can actually have the latest and greatest version of your own projects available on the web. So again, this tool has a lot of functionalities. So you go get the software, you are going to get the latest version. Just a word of advice: you will always need to have the latest version for it to run. So you may run EDSim, after maybe a long time from the last time you run it, and it will say there will be a warning saying you need to download the new version. So, which is not a big deal. You download the new version. You first uninstall the previous version and install the new version, and no issue. It will import your projects as well. So it should be a very transparent process. You accept the license agreement and click accept. And now you are going to get a file that is between 700 and 800 megabytes. This is the zip file that includes the actual installation file of EDSim. So you proceed to install it, and now you have EDSim in your computer. And again, fantastic tool to simulate switch mode power supplies. So with that in mind, now that we have EDSim installed, now let's go through a real-life example. So if I go, and again, I'm in the eDesignSuite website. It is eds.st.com. And as I mentioned, if you already signed in, you're going to see your latest projects. You can see that I have a few of them already in my projects, and you can actually see your whole folder of old projects as well. And we're going to do a real-life example for an industrial application. So we're going to with the help of the eDesignSuite website, we're going to simulate a 24 volt voltage input power supply. So it's going to be a 24 volt in, 5 volt out, 1 amp DC-DC solution. So with that, we go to the power supply design tool, we select DC-DC, and we start a new project. So it's going to take a few seconds to load, and you are going to see the whole portfolio of ST devices available for you. So here we go. There's the whole portfolio of power devices. And so we mentioned that we want to simulate a 24 volt in power supply. So we're going to do a let's say a 24 volt plus minus 20%, and we want 5 volts, 1 amp. So we're not looking for an automotive, we're looking for an industrial solution. And we also look to actually have this simulated in EDSim. So we're going to filter out devices that are not yet integrated into EDSim. Again, the latest and greatest devices should be already there. So with that, we are going to select the DCP3601 CDMR. This is our new industrial buck regulator. It's a 36 volt 1 amp buck that switches at 1 megahertz. So we are going to click on Customize Solution. And we just double check that everything looks fine, 19.2 to 28.8, which is the 24 volt plus minus 20%, 5 volts out with the 1 amp maximum output current. So we proceed with the customization. So what is great about this device? We're still within the eDesignSuite on the web tool, so we actually haven't gone through EDSim. So we're just going to wait a few seconds till the eDesignSuite actually shows you not only the schematic, but also recommends a few other devices, the passives, the actually real-life devices. You can see that from the schematic here, we're using a 15 microhenry inductor. We're using a couple of feedback resistors to set the 5 volts out. We're having a 22 microfarad output capacitor. And below, you can actually see a few preliminary simulation results. The duty cycle, the efficiency, the stability plots, the body plots. And you can actually see a summary of the actual losses between that actually encompasses both conduction and switching losses. So, and with that, I'm actually having another project open here. This is the same schematic, but we are going to now include a different inductor. So we are going to include an inductor from our partner from Wurth, and the device we're going to include is the 74439346515 inductor, which is comparable as the one that eDesignSuite already suggested. So you can see here the datasheet. So it's a 50 microhenry inductor with a 8.5 performance rated current and a 4.3 saturation current and a 28.6 DC resistance. These are the parameters that we need to identify so we can integrate this device into eDesignSuite. And once we click the inductor, these are already pre-filled, but if you actually wanted to, you can actually add a component, and you can actually go and type a new inductor. In this case, it's already captured, so I'm just going to cancel that, but this is the place where you can put the specific part number, the manufacturer, the mount type, and we need just 4 parameters: the value, the DCR, the IRMS, and the saturation current. So, and with that, the simulation is done here on the website. So You can actually go and click around. There's other simulations that you could do. I'm not going to go into that right now. We're just going to be looking at the preliminary simulations down here. What I want to show you is how we can leverage EDSim to play with this design. So, and EDSim is fully integrated into eDesignSuite. So we're going to go to export for EDSim, and we're going to type a file name for this device. And once you download that device, you are going to get a zip file. In this case would be Wurth dcp3601.zip, and you're actually going to get four benches. So in this case, for the 3601, you're going to get a line transient, load step, startup, and steady state benches. So we're going to keep it simple. We're going to go and see steady state. And steady state includes 4 files. It includes a text document, a schematic document, a README file, and a batch file. So that batch file is the one that will help us run EDSim. So, and with that, we go to we have the files right here. We go to steady state, and we click edsim.bat. And what this will do, it will actually automatically call EDSim. It will import the schematic that we just had in eDesignSuite. And here we are. So basically, this is the same schematic we saw on the website. And not only that, actually the inductor that we customized is already here. It's already in EDSim. So this is again, this is the steady state bench, but it's as simple as just run the schematic to run the simulation. And this is the steady state simulation. So we're not going to see the startup. We're not going to see any line or load transients. We're just going to see how the device behaves in steady state. So as you can see, it runs fairly quickly. I'm actually on a not so powerful laptop, and it is done. So you can actually see a lot of the simulation information. So you can see all of the different signals. So in particular, we want to take a look at a V out. And as you can see, we were expecting a 5 volt output, which is exactly what we have here. And you can see that the DCP-3601 actually switches at a 1 megahertz frequency, which is what we see here. That's actually the repo right here. Fun fact, so we actually have many different versions of DCP-3601. We have them in low consumption mode, which basically is PFM. We have it in low noise mode, which basically is PWM. And you can actually see that the specific topology, you are going to see that in EDSim. So let's say if you are actually simulating a PFM with very low output current, which is, let's just say, a few microamps, you're going to see how you're not going to have a constant ripple, because the device will actually be practically off in standby until the output voltage actually goes below 5 volts, and it will turn back on and get back to 5 volts. So again, fantastic tool. So I really invite you to take a look and simulate. What is cool about device and about this this software is that you just saw steady state, but you can also do line and load transient simulations. You can do Monte Carlo simulations. You can do efficiency simulations. And EDSim, again, is very flexible, great tool, totally free. So I hope this was helpful. Thank you so much for your time. I hope to host a more in-depth tutorial on EDSim in the future.
Now we encourage you to test drive these tools and speed up your design process and shorten debugging time. To get started or to find more information, click the links available in the description or visit our website at www.we-online.com/REDEXPERT. We know that while some streaming platforms are making the switch to video format, there are still plenty of listeners tuning in through audio only. If you'd like to learn more, head over to our website where you can test out the mentioned tools and software. You'll also find all the images, demos, and diagrams we discussed in today's episode at www.we-online.com/podcast or visit the Würth Electronic Group YouTube page. You're listening to Würth Electronics What's Up Radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Electronic technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up podcast.